Example 4.3. In this example, we have a turbine blade, which is exposed to turbine blade, which is exposed to a turbine blade. The blade is exposed to a air channel. The blade also has air channels within convection taking place. Notice that we have convection taking place at the top, another convection taking place at the top, and we also have convection where it has taken place in the inside, where it has convection taking place in the inside. The test that we have to determine the temperature distribution inside of this limit temperature display. Notice the inside of the blade is symmetrical. Notice that basically the blade itself and the areas around the channel are shaped in the channel, or we have the channel corners are the areas around the channel, the four corners are basically the mirror image. We're going to select the four corners are basically we're going to select the upper left corner here over the air channel. We're going to select the first here that we are going to do. The first is to determine that we are going to do is to determine the first task that we are area that we have. So we take to determine the area that we have divided. So we take the area x in this case divided delta y. In this delta x we take delta y and delta x equal to 1 case we take delta y. We are going to develop equal to 1 millimeter. We are going to develop the equation for each one of the notes, and then we're going to develop each one of the notes, and then eventually different equations for each one of the notes. We're going to consider this the temperature distribution. We're going to consider this two-dimensional steady. We're going to two-dimensional. We're going to calculate radiations. Two-dimensional to have radiation, and we're going to have radiation, and we're going to have heat generation.
The next step is to determine the boundary condition of each of the surfaces. Notice that the surfaces that use for symmetry, they now become insulated, therefore they are adiabatic, and they're shown in yellow. The remaining surfaces are exposed to a fluid, therefore they are under convection. The one in green is exposed to the hot gases, and the one in blue is exposed to air. The next step is to determine which nodes have the same boundary condition and determine the finite difference equation for each one of them. These nodes are located in a corner. They are exposed to insulation, conduction, and convection. The convection is to the hot gases. If we do a balanced equation in each of the nodes, we will be able to get the following finite equation. For node 1, we get T2 plus T7 minus 2 plus H0 delta x k times T1, that is equal to minus H0 delta x k times T infinity 0. Notice that in this case, the surrounding nodes are T2 and T7. The same equation could be obtained for node number 6, and the nodes that surround there are going to be T5 and T12. And the structure of the formula remains the same. This is going to be T6, and the constants are going to be exactly the same. The other nodes that we have are node 18 and 21. These two corners are also exposed to insulation, conduction, and convection. The difference between these two nodes and node 1 and 6 is that instead of being exposed to the hot gases, they are exposed to air. So the quantities are going to change are basically just the values of H0 and T infinity 0. So we write the equations for node 18. Notice that the surrounding nodes are going to be 12 and 17, so we simply say T12 plus T17. The structure is basically the same. Now it's simply HI for the inside, delta X, K, and this is T18, and this is minus HI, delta X, K, T infinity I. We do the same process for node 21, and we find the nodes that are surrounding it are 15 and 20. So we write T15 plus T20 minus 2 plus HI delta XK T21 is equal to minus HI delta X K T infinity I. Please make sure that you go back and are able to derive the equation for a corner with adiabatic conduction and convection, and you get exactly the results that we have over here. We have over here the list of the nodes that we have accomplished so far. We're going to continue with the nodes that are exposed to symmetry, therefore they have insulation surface boundary condition. These nodes are going to be 7, 13, 12, and 20. Notice that they also are located in the plane. So the final difference equation for them is going to be, for number 7, we have that the surrounding nodes are going to be 1, 8, and 13. The equation becomes T1 plus T13 plus 2 times T8 minus 4 times T7 is equal to 0. In the same format, we write for 13, and we write the adjacent nodes are 7, 14, and 19. So we have T7, T19 plus 2 times T14 minus 4 times T13 is equal to 0. We do it now for node 12, and the adjacent nodes are 6, 11, and 18. And we write T6 plus T18 plus 2 times T11 minus 4 times T12 is equal to 0. The next node is number 20. The adjacent nodes are 19, 21, and 14. And we write it T19 plus T21 plus 2 times T14 minus 4 times T20, and this is equal to 0. Please go back and make sure that you're able to derive these equations. The next set of nodes that we're going to derive are going to be the interior nodes. These nodes correspond to 8, 9, 10, 11, and 14. The equation should be, for 8, the surrounding nodes are going to be 2, 7, 9, and 14. Therefore, the equation becomes T2 plus T7 plus T14 plus T9 minus 4 times T8 is equal to 0. For node 9, the surrounding nodes are 3, 8, 15, and 10. Therefore, the equation becomes T3 plus T8 plus T15 plus T10 minus 4 times T9 is equal to 0. The next node is number 10. The surrounding nodes are 4, 9, 16, and 11. So we write it as T4 plus T9 plus T16 plus T11 minus 4 times T10 is equal to 0. Next node is node number 11. The surrounding nodes are 5, 10, 17, and 12. Therefore, we write the equation as T5 plus T10 plus T17 plus T12 minus 4 times T11 is equal to 0. The last node is number 14, and the surrounding nodes are 8, 13, 20, and 15. Therefore, the equation becomes T8 plus T13 plus T20 plus T15 minus 4 times T14 is equal to 0. Once again, please go back and make sure that you're able to derive each one of these equations. The next set of nodes that we're going to evaluate are going to be in a plane exposed to convection and to conduction. These nodes are going to be 2, 3, 4, and 5 exposed to HO and T infinity O, and number 16 and 17 exposed to HI, T infinity I. Let's start with node 2. The surrounding nodes are 1, 3, 8. And the equation looks like T1 plus T3 plus 2 times T8 minus 2 times HO delta X K plus 2 times T2 is equal to minus 2HO delta X K T infinity O. If we write the similar equation for node 3, the surrounding nodes are going to be 2, 4, and 9. So we write 2 T9 minus. The structure over here remains exactly the same. This is T3 minus 2HO delta X K T infinity O. The same structure goes for node number 4, and the surrounding nodes are going to be 3, 5, and 10. So it's 3, 5, and 10. And the rest of this structure looks pretty much the same. This is T4 minus 2H0 delta XK T infinity O. For number 5, the surrounding nodes are going to be 4, 6, and 11. So it's T4, T6, T11. And once again, this structure remains the same. Plus 2 T5 minus 2HO delta XK T infinity O. For nodes 16 and 17, we use exactly the same equation. The difference is instead we're going to use HI and T infinity I. So let's define it for node number 16. The surrounding nodes are going to be 15, 17, and 10. So T15, T17, and T10. The structure remains the same. Once again, the difference is HI. This is T16, 2HI, so that's the convection that is exposed to, and T infinity I. Let's do the same thing for node number 17. The surrounding nodes are 16, 11, and 18. So it's T16, T18 plus 2 times T11 minus 2 HI delta X 2 plus 2 T17 now minus 2 HI delta X K T infinity I. And these are the nodes once again for convection plane. Please make sure to go back and able to do each one of these equations. The next node we will evaluate is number 19, which is a corner that is adiabatic. The surrounding nodes are going to be 13 and 20. Therefore, the equation looks like T13 plus T20 minus 2 times T19 is equal to 0. The last node that we have is number 15, which is an internal corner which is exposed to convection. The surrounding nodes are 21, 16, 14, and 9. The equation is given as 2 times T9 plus 2 times T14 plus T16 plus T21 minus 2 times 3 plus HI delta XK T15 equal to minus 2 HI delta X or K T infinity I. Please go back and make sure that you're able to get these two equations. Once you are done with the derivations, you're going to notice that you have 21 different equations for 21 different unknowns. The method that we're going to solve is to create a system of equation in the form of AX equal to B. Then we're going to solve the system for X by simply taking the inverse of A times the vector B. The first step is to create the matrix. The matrix is done in MATLAB in this form. I simply set up all the constants that we had given by the problem, and then I create each one of the rows independently. So this is for node 1, node 2, and so on and so forth. Notice that in the equations we have the different coefficients multiplied by the particular nodes that are adjacent to the node that we're looking for. So for example, for node 1, we have a node 1, the adjacent node is 2, then we have 6, and the rest of the values are 0. You have to do this process very patiently and carefully to make sure that all the rows have the same amount of components, which is 21 in this case, and they have the proper sign. Then you set up the vector B with all the constants, which are set up to the right side of the equal sign. Once you have all the rows, I set up the matrix by simply putting all the rows all together. And then I set up the vector by putting all the components of each one of the nodes. Then I set up the solution of the temperature, simply inverse of N times B. I'm going to execute this file, and this is the solution I get. Notice that I have 21 different solutions, and in the way that MATLAB provides the solution, it has a factor of 1 times 10 to the 3. That means that each one of them is, for example, the first one is 1526, and so on and so forth. Please make sure that you are able to set up the solution in MATLAB in the same way and able to get the same solutions. Now that we have the temperature solutions, I'm going to show you how to plot it in MATLAB. The solution, we have it in a column form. We need to create a row that includes all the particular nodes in the grid that we need. Notice that we need to have a square grid, so we need to add temperatures at the points that we do not know after the node 21. The temperature of those nodes is equal to the temperature infinite I. So what we do is we create a row vector that has the temperature that we obtained in the previous step, and we create 3 different nodes with temperature of T infinity I. The next step is we're going to resize the vector so that it has the orientation that we have. We have it so that it has 6 nodes going across one direction and then 4 nodes in the other. So we reshape this vector so that it becomes a matrix, and the size is going to be 6, 4. So that means that it's going to be 6 columns and 4 rows. The next step to plot it, we need to create the vector that it has for the x and for the y-axis. For the x-axis, we start at 0. We have we go up to 6 millimeters, and we have 6 divisions. For the y-axis, we start actually at 4 to 0.
because we're doing the other orientation, since we started the labeling of the nodes in the upper part of the y-axis, and then we have 4 divisions. The next step is to create a mesh grid. Once you have done this, you create a mesh plot or a surf plot, and you could use the following description so that it could actually fill up the color. And then to make sure that we get the front view of this plot, we set view 2. Once you are done with the selection, we run it. This is the temperature distribution for the blade in that cross-section that we created. Notice that as we predicted, the higher temperature is going to be closer to the surfaces that are exposed to the hot gases, and the lower temperatures are going to be closer to the air in the channel. However, the temperature distribution is actually around 1500 Kelvin, so that's why there is not a high gradient within the distribution that we see in this plot. Please make sure that you follow all the steps, derive all the equations, be able to solve the system using inverse of the matrix times B, and be able to plot the temperature distribution of this problem.